Alright, we have these numbers, okay, in different years. Now let's compute this table, okay. How to do the table? Same thing. Using these values, do subtractions and give us absolute change, okay. So what is absolute change between these 2 years? New minus old. What do you get?
108.
108, very good. Absolute change, new minus old. Do it, please. Use a calculator, do it. New minus old.
Which one are you on?
I want these two,
Okay.
between year 1 and year 2.
Is $114.48.
Okay, 114.48. Good. Absolute change, new minus old. $121.35, right? New minus old. Everybody? Yeah, just, compute relative change, okay? How? Use absolute change divided by the old value, okay? So we're not comparing what? These two values, compute a relative change, okay? From this value to that, from this number to that number, okay? So use absolute change 108 divided by what? Old value 1800. To do this two, use absolute change old value 1908. Well, similarly, please really calculate the making them and let me know your results, okay, in decimal numbers, okay.
0.06.
You get a 0.06 here? Okay. How about the second relative change here?
0.06.
0.06? Make sure you do every one by one. What do we get, guys? 0.06, 0.06. Oh, so far we can see that for this model, does absolute change, these values remain the same, stay the same? No. However, relative change, this column, the same, right? And then what will be the percentage change from the previous year? 6%, 6%, 6%, and 6%. Right? Why? Because it says Oliver will, deposit what? 6% more than more than his previous year's deposit, right? Okay, so let's answer these, 3 questions quickly, okay? How are the total of deposit changing from year to year? What is the mathematical rule to find the next year's total amount of the deposit? What is a change? How are, those deposit change? 6% more from the previous year, okay? So I'm going to say increasing by 6%, okay? And how can we compute the next year's amount of deposit. Multiply the previous year, okay, by what? Previous year's amount, okay, by what? 1.06. That's what we did, right? Remember how we got these numbers? From the previous year multiplied by 1.06. So that's how we get these numbers, right? Or 106%. Just say 1.06. Okay. Question 11. Which value stay the same? Absolute change or relative change this time? Relative change. Without continuing the table, how can you mathematically find the amount of the total of deposit in the 6th year? From the 4th year times by 1.06 give us 5th year. And use that result times by what? 1.06 again. Okay? So mathematically we could say it's going to be what? $1,800. We times by 1.06. First time it gave us this result, right? Remember 1,800 times by 1.06 give us this. And from this result times by another 1.06, which is the same thing as 1,800 times by 1.06 square, it will give us at the end of the 2nd year this. You can try, okay? Using this result times by another 1.06, we get this. And then at the end of 4th year, 1.06 for 4 times. 5 year, 1.06 5th times, and then 1.06 6 times. Okay, so I would say to find the deposit in the 6th year, we will compute 1,800 times by 1.06 to the 6th power. Okay, guys, let me ask you, what is the order of operation if we encounter both multiplication and exponent? Which one should we do first? Multiplication? Exponent. Okay? So that means when we do the calculation, we have to use a calculator to do 1.06 to the 6th power and then multiply the result by 1,800. Do you know how to do that on your calculator? Do you know how to do the exponent? Different calculator may have different, buttons. Okay? Some of the button looks like this, give us the, a hat. Give us the exponent. Some of the calculator, you have a button with x to the y power or y to the x power, something like that. You have to know how to do large exponents, powers. Okay. All right. Now, I'm going to ask another question. How can you mathematically find the amount of total of the deposit in the 10th year? What do we do? Use 1,800 times by what? 1.06 to the what? 10th power. Okay. All right, now we have these conclusions. Okay, I'm going to ask volunteer to read everything above question 13. Okay, so whose turn? Morgan?
When the relative change is the same from time period to time, the mathematical model is exponential. Exponential growth model is the amount equals initial amount times the growth factor to the time period. One way to find the growth factor can be found by using the following formula. Growth formula equals 1 plus percent change. 13, use 1 plus percent change to find the growth factor for the total amount of the deposits.
Okay, fine. Okay, yeah, good. Thanks. Exponential growth model. Okay, what can we call a model is exponential? If what? The relative change is the same. Okay, remember, compared with the previous one, absolute change gave us linear model, and relative change remains the same, give us what? Exponential model. Okay, so exponential model is defined by, in order to compute the total amount, we let it equals what? Initial amount. In our current question, it is 1,800, right? That's an initial amount. Times by what? Growth factor. What is growth factor in this current problem? 1.06. Okay, 106%, right? That's a growth factor to the what? Times period. Okay, after 6 years, to the 6th power. After 10 years, 10th power, and so on. Guys, do you see that? Okay, so I want you guys to really understand this, okay? Initial amount times by growth factor to the times period, okay? Now, growth factor, okay? How can we figure out the growth factor in the exponential model, okay? There are two ways, okay, to find the growth factor, okay? So, two methods, okay? Method 1, to find the growth factor is by using 1 plus the percentage change. What is a percentage change in this question? Is it given? Percentage change? Is a percentage gain in the question? It's already given, every year, okay, it's going to be 6% more than the previous year. So what is the percentage change in the question? 6%, okay? So, question 13, use 1 plus percentage change to find the growth factor for the total amount of the deposit. What is the growth factor in the current question? 6%. Yeah, growth factor equals what? 1 plus 6%, which is 1 plus what? 0.06 gave us what? 1.06. See? Growth factor. And then we put it in the model. This is method 1, 1 plus percentage change for just the growth factor, okay? What is the second method to find growth factor? I believe we are very familiar with this second method. What is it? By taking the ratio of every 2 consecutive data points from your table. Okay, growth factor is defined to be what? For every 2 consecutive data points, use new value divided by what? Old. Remember how we did it? Okay, how we get the new value? Use old one times by 1.06. Give us the new value. Now the growth factor can be calculated by what? Every new value divided by old value for consecutive, okay? Then we also get a growth factor. Question 4, use 2 consecutive values from our current model to show the growth factor. How? These are our values. Just pick up any arbitrary 2 consecutive ones. Which values do you want us to pick? Any one of these values. Which one do you want to pick? Just pick up 2 consecutive. So I would say let's do this one and that one, arbitrary. What is old value? Old value. This one. What is the new value? This, right? So use the new value, divide by the old value, and see do you get a 1.06 or not, okay? So I'm going to copy those 2 numbers here. They are 2143.83 divided by what? 2022.48. Use your calculator and see whether you get a 1.06 or not. Yes? What do you think about this method too? Very naturally, right? New value divided by old, give us that. Or use what? Method 1 give us what? 1 plus the 6%. Also give us 1.06. Okay? Okay, see it has now having a relative change of 6%, okay, or growth factor of 1.06 are all different ways to study the same relationship, okay? Well, see guys, from the current model, we get this, right? Amount equals 1,800 times by 1.06 to the 6th power. Compute this thing will give us what? The answer for the deposit after 6 years, okay? But here, I want to emphasize that, okay, just like we said before, we have to do the exponent, then multiply the results, this result, by 1,800, and then we will get this. Everyone? So now we introduce the linear growth model, okay? Linear growth. You guys supposed to good? Okay, so this is the growth model, question 15, 16, 16, you can try them, okay? Now let's turn to page 111, guys. Let's talk about what? exponential decay. Okay, so what do we have a growth model? And what do we have, what we call the model is decay? If the percentage change is an increase, that means from the previous question we have a 6% more, right? The percentage change is 0.06 or 6%. Then we have growth model. When will we have a decay model? Yeah, if the percentage change or the relative change is what? A negative number. Sometimes we have negative relative change, right? Remain the same, right? So that, if that's the case, we'll have what? A decay model, okay? We'll have a decay model. Okay, so let's look at the decay model, okay? Exponential decay model is defined very similar to the growth model, okay? It is defined to be, okay, initial amount times by decay factor to the times period, okay? And to find the decay factor, there are also two methods to do it, okay? Method 1 is what? Use 1 minus the percentage change, okay? Yeah, so you'll see that we have a negative, relative change, okay? So 1 minus percentage change, say we have a 6% less or decrease, then we use 1 minus 6%, okay? So decay factor, either use this method or what? Still use what? Every 2 consecutive data points, use new divide by old. Still, second method remain the same, okay? New value divided by old value will give us the decay factor, okay? The decay factor will be a decimal point less than 1. Why? Because 1 minus a percentage change, okay? Remember from the previous growth model that, question, what is a growth factor? 1.06. That decimal point is greater than 1. Decay factor, the result will be less than 1. Okay, you'll get a less than 1 result for your decay factor. Okay, and then new value, because the values are decreasing, so the new value is smaller than old value. So, of course, new divided by old will also be a less than 1 decimal point. Okay, okay. Now I would let us try an example. Okay, how about we try this question 1 on page 111. I'm going to ask a volunteer to read this entire question for us. Andrew.
Airline miles have a tendency to lose value over time as airline companies change or update policies. Alicia traveled often for business and had earned 500,000 frequent flyer miles prior to her retirement. She estimates that her miles will lose around 26% of their value, from year to year. What is the decay factor? What is the unit of time? Construct an exponential model to approximate the value of her airline miles for any given year. Airline miles will remain time after she retires.
Okay, very good. Thanks. So let's try the questions. Okay. 500,000. What is this? Initial what? Initial value since retirement, right? And then after retirement, she estimates or expects that her miles will lose 26% from year to year. So what is the unit of the time? In a year or in a week or in a month? How does the time change? Yearly, right? Yearly, okay? So years. It's not like every month lose 26%. Not every day lose 26%. It's every year lose 26%. So the unit of time is in years. Okay, it's scaling, right? From year to year. What is a decay factor? How do you find a decay factor? There are two methods. Now in this question, which method can we use? The one, because it told us what? The percentage change is what? 26% less. Okay? So decay factor should be what? 1 minus 26% in decimal number, 0.26, right? So what do we get here for our decay factor? Point what? 74. See? This number is less than 1. Okay? Construct an exponential model Okay? So the mileage, okay, the mileage will equals initial amount times by decay factor to the times period. Okay? So what is initial amount in this question? 500,000 miles, right? Times by what? Decay factor, what is that? 0.76 to the what? T's power. Here, T is the time in years. Okay, so when, where? T is time, okay, in years. Since retirement. Okay, yes, since retirement, after each year, 26% less. So it will be what? 74% of the previous years, right? Okay. How many mileage will remain after 5 years of retirement? What do you do? Replace this T by what? 5. Okay, so let's compute that. To the 5th power. Remember, I always do the exponent, right? And then multiply by 500,000 in the second time, okay, in a later time. Okay, after you get this. Have you got any what do you have?
110,950.
Miles, right?
Yeah.
So far so good, everybody? Okay, so I would say that, these are the exponential growth and decay model, and then I will give you some time to practice, okay? So except for those questions, okay, that I assigned, I'm going to add more for you, okay? For the models, okay? For the model. So guys, let's turn to page 113. I'm going to add the entire page of 113 for us. Okay, add the entire page for 113. Okay.